Alright, in the previous video we started talking about simple harmonic motion and how we take these motions in the real world and we project them or map them onto this phase space, which we can then relate back to what's happening in this real space. What I wanted to do to start this video off is just, I felt bad because I drew this eye off to the side and it was kind of embarrassing that you couldn't see it then, but also it's kind of embarrassing how bad the eye is. This is such a better eye. So I just wanted to point out that I did have an eye over here. But I'm almost glad that I didn't show it to you initially because it's just not very good. In any case, we had ended the last video with this y equals the amplitude times cosine theta, and v equals the maximum velocity times the sine of theta. The problem that we run into is, first of all, what goes on with the acceleration. And it turns out that the acceleration would just be sort of the maximum acceleration times the cosine of the angle also, except if this is a positive value, these would then tend to be negative values at those locations. And hopefully this can make sense. I think these two here will be pretty easy to explain. So let's just go and look at this here. So for instance, down here at the bottom, there's going to be a super big spring force upwards and kind of this measly small gravitational force downwards. Up here at the top, we're going to have still that same small gravitational force downwards, and probably a not quite so large and impressive, but still present spring force downwards, trying to push this down. For instance, if this is a spring that is able to be compressed or stretched. In many cases, what will actually happen is that the spring actually might still, whoops, I don't know what I just did there. Let me redo whatever there we go. Okay, so in many cases what actually happens is we would end up with this sort of gravitational force down, and we would end up with this really nice and big spring force up, and then up at the top we might actually still have a little tiny bit of a spring force up and that same force of gravity down, so that the net force in each case is approximately the same. And I'm just going to extend that gravity a little bit more and extend this one a little bit more, so we get that the net force in each case, which I'll make yellow, the net force in each case would look something like this. Okay, so that our net force at the top and at the bottom would be the same. But as we get towards the middle, we would have an equally sized gravitational force down and spring force up. And so here we would get a net force and thus a net acceleration equal to 0. The point that I want to bring up with the negative signs is that if my amplitude is positive, my net force is going to be negative. If my amplitude is negative, my net force is going to be positive. The negative sign here with the velocity is a little bit trickier, but if I start off with this positive displacement, right away, even as my displacement, my position is still positive, it's just getting less positive. It's getting less positive because the vertical component of the velocity would be downwards. And so that's where this negative sign comes into play. So hopefully you understand kind of the basics of this as far as the spring goes. What I want to do is I want to talk about this theta, because normally it wouldn't really make sense to talk about the position, let's say, of a spring in terms of some imaginary angle. So instead what we do is we talk about it in terms of some imaginary angular speed, because that just frankly makes more sense. And hopefully it will in a moment, because I want a position as a function of time equation. And I can do that if I relate it to angular speed. Hopefully that makes sense. So I've got this thing here, and it's going in a circle, right? Going in a nice uniform circle. And so I can say that the angular speed, let's try again, the angular speed would just be equal to theta times time, which is pretty simple. And we're assuming that this is going in uniform circular motion, which means that this is constant for the object going in uniform circular motion. So that's our angular speed. However, we feel awkward about describing the angular speed of something that's just bouncing up and down, clearly not in any sort of a constant speed manner, as a constant angular speed. It's just weird. So we console ourselves by changing the name of omega. When we talk about in phase space, it's angular speed. When we talk about it in real space, we call it angular frequency. And this makes us feel better about what we're doing. I can hopefully explain what I mean by this a little bit. Let's say that it takes like 2 seconds to go around in a circle, right? So this takes 2 seconds to complete one circle, which is the same as this taking 2 seconds to start up here, bounce down, and then bounce back up. So that's the period. Okay? So we have a period, in this case, equal to 2 seconds. That means that we have a frequency equal to half of a second. Nope, half of a cycle per second. There we go. That actually makes sense. One of the things that we can do is we can relate omega to 2 pi divided by the period, right? Which we could also then relate to 2 pi times the frequency. And the reason why we can do this is because in the time that it takes to complete one circle, which is 2 seconds, it completes 2 pi radians of motion. So that's the distance, angular distance, that's the time. And because the frequency and period are inverses, I can actually also describe that as 2 pi times f. And so what we can do is we can say, you know what, I know that this is angular speed for an object going in a circle, but anytime anything has a frequency, I can describe it also as having an angular frequency, which would just be an angle of 2 pi times f. It's a little bit strange, but that's how we do it. And then we end up with a formulation that looks like this: a cosine of omega t. You may have seen in trig class or in pre-calc something along the lines of 2 pi f times t, which is exactly the same thing as this angular frequency. And to give you an idea of what this looks like then, if t were equal to 1 over f, so basically if we waited until it had completed one complete circle, and that was our time, so our period was completed, then this whole term would cancel out, right? This would just be 1, and we'd be left with the cosine of 2 pi, which would suggest that we were right back where we started, which is exactly what we want. If the period instead was half of, if the time that we've let pass was half of the period, then this would cancel out, but there'd also be a 1 over 2. And so we'd end up with a cosine of pi, which would put it down here and give us our maximum negative amplitude. So that's kind of the basic premise mathematically behind how this works. And we can then actually just plug in the omega t for here. So this would be omega t, and this would also be omega t. Now what I'm going to do in class, I'm not going to get into it right now, but what I'm going to do in class is talk about how we can find omega. And this is going to vary depending on whether it's a spring mass system, whether it's a pendulum, or anything else. So this is the thing that changes. What doesn't change is the basic construct, the basic formula behind how this works out. Now there's one last thing that I want to point out because it's kind of super awesome. So I had this equation, y of t equals x max. I'll do x max. That doesn't actually make sense because that's y. So y of t equals the amplitude times the cosine of omega t, and we had that the acceleration as a function of time was equal to the opposite of the maximum acceleration times the cosine of omega t. If you look at this, there's a couple of things that you'll notice, which is that I have cosine omega t in both cases. The other thing is that hopefully you know by now, and this is one of the few times I'm going to use calculus, but most of you know that this is the second derivative of that. So what I should be able to do is realize that if I take the derivative of this once, that would give me my velocity. So I would have omega, the opposite of omega, times the amplitude, times the sine of omega t. And if I take the derivative of that again, I would actually get the opposite of omega squared, a cosine omega t. And if I look at this, these two here, and actually I guess this wasn't going to be a shorter video, but in any case, if I look at these two equations here, this one here, those are exactly the same terms. So the only reason why the acceleration, and this is v of t, the only reason why the acceleration is different is that we've multiplied the x value, or the displacement value, by the opposite of omega t. So our basic formula actually for simple harmonic motion is that if I take the opposite of omega squared times x of t, I get a of t. And omega is basically describing properties of, in this case, the spring mass system. And we'll talk about those later. But this is the fundamental equation of simple harmonic motion. And what it says is quite easy to interpret. Basically, we always have to have an opposition between the displacement and the acceleration. They will always act in opposition to each other. So if the displacement is small this way, the acceleration will be small in the other direction. If the displacement gets larger, the acceleration in the opposite direction will get larger. So it's constantly trying to bring it back towards equilibrium. And the further away it strays from equilibrium, the harder the system pulls to bring it back in place. Now, of course, once it gets brought back to equilibrium, at that point, because the acceleration had gotten so large, pulling it back, it's going to be moving down, and so it's going to overshoot. So that's kind of the sad part of simple harmonic motion, is that it's always going to lose. It's always going to try to bring something back to equilibrium, and as soon as it gets it there, it's moving too fast to stay there, and so it has to do the whole process over again. So hopefully this makes sense as far as the premises behind simple harmonic motion. And I'm sorry the video ran a little bit longer than I had wanted it to, but hopefully going through the mathematics step by step makes it make sense.